Hello, I'm Mike Douglas, and this is the New Technologies in Mathematics seminar of the CMSA at Harvard University. And today we're delighted to have Tony Wu, who's from Stanford and Google AI, and he'll tell us about memorizing transformer, an improved language model that can also couple to a database and improves its performance on a wide variety of tasks. So as I always do, I'll offer to read the chat. And if you want to ask a question, you can put it into chat and I will raise it. But the speakers also offered to answer questions through the talk. And there'll be, of course, time for questions at the end. So with that, Tony, please begin.
Thank you. Thank you, Michael, and also for inviting me. Yeah, so my name is Tony, and I'm currently a joint postdoc from Stanford and Google. So today I'm going to talk to you about the recent work from our Google group on memorizing transformer. And yeah, so I guess please ask questions throughout my talk. I have prepared a pretty, I guess, not very long talk. So like if you guys can just chime in and ask questions, I'd love to have these kind of discussions. All right, so let's get started. So the main problem that we want to tackle is this growing knowledge base, which is something that is pretty useful in many reasoning applications. For example, I guess for the folks here, this is the most relevant application, which is in mathematics. You always need to look up, the function, the lemma names and definitions, and also in the case of like program synthesis, you need to deal with a huge code base. So you need to look up, let's say, the function definitions and etc. So to be more precise, when you sort of start to write mathematical papers one page at a time, and you're basically trying to prove these intermediate lemmas along the way, and those are basically your knowledge base, right? You're keep growing your knowledge base until eventually you try to prove a theorem that needs to referring to all these previous lemmas that you have proved. So as a human, we have a way of somehow access our knowledge base, and also have a way of sort of growing this kind of knowledge base and allow us to immediately utilize these things in the knowledge base. But with the current, the mainstream approach that relies on transformers, this becomes a pretty big bottleneck. The reason is that transformers can only deal with a limited context window. So usually this context window is only about like a page, meaning that now, okay, so when you're writing those math papers, you're also forgetting what you wrote, in the past. And so this becomes a big problem when we try to use machine or these like language models or these AIs to prove theorems, because at the moment, for example, for this proof, you don't even know where these lemmas come from. You don't have them in your knowledge base, and you cannot really refer to them. So this work is really trying to sort of provide a solution to this. And to understand this problem better, let's take a look at the real reason why this becomes a problem for transformers. So transformer essentially operates on a finite context window. So usually what it does is that if you have a long sequence, you will basically chop it up into chunks of a chunk of sequences, and then you read only a finite a fixed window size. And for example, in this case, you only can look at these tokens in your sequence, and this becomes a problem when you try to refer to some names outside of the window. And the main reason why this is the case is because there is a quadratic complexity, computational complexity, with respect to the context window size. And just to explain this in more detail, we can take a look at what exactly is a transformer. So a transformer is essentially a model, it's a neural sequence model that operates on sequences. So it takes in an input as a sequence, and it has a couple of transformer layers on top until you eventually output another sequence as an output. And inside of each of these transformer module, a transformer layer, there is this famous self-attention mechanism. And so the self-attention mechanism is as follows. For each of the token in your sequence, you will generate three things. So they are a query and a key and a value. And what I mean by generation, meaning that you basically have a neural network that generates these continuous embeddings that represents a key vector, a value vector, or a query vector. And you then use the query vector generated from each token to attend to the key of the other tokens. And this is done through a dot product. So you basically compute like a score for each of the token to every other token. And this score represents how relevant these tokens are. So that essentially now if you have, for example, this token I here, and you attend to all the neighboring tokens in your sequence, you then can form all those scores. And those scores represents how important or how relevant this query is to all the other keys in your sequence. And you can do like a softmax, meaning that you can then normalize it so that it becomes a probability distribution. And eventually your next token representation will be the weighted sum using these soft values with your value vectors. So this is how you compute a transformer layer or a self-attention layer. So the main point here is that the self-attention mechanism is essentially like you try to sort of merge the information in the current sequence in a way that you want to sort of extract the most relevant information or the most relevant tokens in your sequence and integrate them in this kind of a soft attention manner. But this is exactly the reason why we see this quadratic explosion, because now you need to attend from each of the token to every other token. And this becomes, this quadratic complexity that is a pretty big bottleneck for computing transformer to compute the transformer layer. Yeah. Is there any questions up to now? So up to this point it's really just the background of like what the transformer is and where the quadratic explosion comes from. Okay, so basically this is reason why we couldn't extend our knowledge base. We can only use a finite or a fixed window size. So in this work, what we do is we introduce a memory, and this memory will essentially maintain all the previously generated keys and values. So again, at every layer, at those self-attention layer, you will generate those keys and values and query pairs. So we're basically for the previous chunks of sequence, we'll then store all these keys and values. And so now, if you have this memory, even though we still operate on chunks of sequence, we can then use, when we attend to, when we are operating on the current sequence, current chunk, then we can then attend to the memory. So we can then retrieve information from the memory. So this allows us to not only constrain our attention to the current chunk, but also have access to all the past information. For example, if you're reading a book or reading a math paper or trying to prove a long theorem, the memory will be keeping track of all the previous information, or like writing a code, for example, then so that when you try to predict the next token, you then have access to the previously generated keys and values. and that allows you to predict the next token, for example, in this case.
Sorry, can I ask a question?
Yeah, sure. Yeah.
Sorry, go ahead. Okay, I'll go first. Two small questions. First of all, what's the typical size of a window? Just
yeah, the typical window size is something around 2048 tokens. So that is usually about a page of paper, I guess you can say. Maybe think of like that. Yeah.
I see. And the memory, is it similar to the way you generate basically a summary of some text? I mean, is it the same idea?
So I may so the next several slides will explain exactly what the memory is. So maybe you can save that question for later.
Yeah, sure. Thanks.
Yeah. Mm-hmm.
Yeah, I'm wondering whether this is in training or in testing.
So this is both for training as well as testing. Yes.
Then in training, like when does the optimization step happens, and like after, like do you update the content of the memory?
No, that's a very good question. So essentially, okay. So I think I see there are two problems. The two questions. One is whether we're updating the memory. Yes, we do update the memory. So basically, what we do is we process, a sequence of long text and in chunks, in consecutive chunks. So we, for example, read, even during training, we read like, a book, for example, starting from the first 2048 tokens to the next 2048 tokens, et cetera, and et cetera. So when we, go from the first 28 to the next 28, before we go to the next 2000 tokens, we will update the memory with the current generated keys and values, if that makes sense. So I mean, there's another problem, which is maybe you're asking, because we're optimizing this along the way, so the previous keys and values becomes probably stalled. They're like generated by the old parameters. So yes, there is some training stability problems, which I will also discuss later. But yeah, so that's a true concern. However, in most of cases, when the memory is not super large, we haven't yet seen any issues with this so far.
Does the optimization step happen between each chunk, or like after you read the entire very long book? Yeah.
So the optimization does happen between each chunk. So we don't. So for example, we only read 2048 tokens at a time. So in between the 2048 tokens, we will do our optimization step.
I see. Thank you.
Yeah. So another detail, or not, actually not a detail, this is a very important component of this architecture, is that when we attend to the memory, we use something called we use k-nearest neighbors to do the memory attention. So what this means is that instead of doing a full attention like before, instead of doing like a weighted sum over all the keys and values in the memory, we will issue a query and to find the most relevant keys and values in the memory, and only retrieve the top, let's say top 32 keys and value pairs from the memory to do that softmax sum. So the details will be explained in the next several slides. There seems to be an echoing. Or
I even forget what KDS does.
Okay. Yeah. So basically, so this KN attention allows us to scale up the memory, because there are these very fast implementation of the maximum inner product search. So what we're doing essentially is like we are given a query, we want to find the most relevant keys and values, and this is essentially the maximum inner product search procedure. And these, so there exists a very efficient implementation of these, where the computational complexity is only about log n, where n is the size of the memory. So this hence allow us to scale up the memory to a very large size.
And can I ask a quick question on that? Is this
Sure,
an
sure.
exact nearest neighbor search?
No,
or
this is approximate.
it's
near,
approximate,
yeah,
okay.
yeah, that's right. It's an approximate nearest neighbor search. That's right. So usually you can do some kind of clustering to sort of speed up your search. Okay, so lastly, there's one last detail here, which is we don't backpropagate into the memory when we train the system. So basically, memory are kept as like a non-trainable parameter in your network, and you can essentially attend to it, but you don't really backpropagate into it. The reason for that is, if you want to backpropagate into that, then you need to keep track of all the previously generated activations, which are just too large to be maintained. And this is for a reason for scaling the size of the memory. Okay, so just I think I need to for the next several slides to explain to you how the memory exactly, what does it look like. So I hope this next several slides will make things more clear. So again, we're given a long sequence, and like in transformer, in the case of transformer, we still chunk it into a couple of chunks. But unlike in transformers, where you just randomly shuffle these chunks, we keep the orders of the consecutive orders of chunks. So basically, we're reading one chunk following by the next chunk in the sequence. And so in the very beginning, there's no memory there's nothing in the memory. It's an empty memory. So when we generate the first 20, 48 keys and values, we will then update the memory with those. So essentially, we'll put those keys and values into the memory. And at this time, there's nothing to be attended to. So this is going to be exactly the same as a vanilla transformer. But now the thing that's different is when you go to the next chunk, there is already the memory already inside, which stores the keys and values that's in the first 28 that's in the first chunk. So then you update again the second keys and values into the memory. And also for these tokens, you can hence sort of attend to the keys and values in the first chunk. So in the first memory. So this is how you update the memory. Essentially, you when you go through this long document, one chunk at a time, you're saving or you're storing these keys and values into the memory. And now, given the memory, what we can do is that previously we only attend to the context using the keys and the query and keys dot product, and using that to form a softmax and a weighted sum over the values. And now those queries can now also do a top K attention. So again, this is using like a fast maximum inner product search into the memory. And then what we do there was that we retrieve the top K keys and values that basically means that these keys will attain the top K score when you dot product with the query. And again, the reason for doing this is that you can now scale this up to a very large size of memory without worrying about the computational constraint. And as you also observed, this is an approximate k-nearest neighbor search. So this is essentially this is how we attend to the context and the memory. And now, just to be more precise, previously we have the next token will be only a function of the current context using the attention module. But now we have a memory module, and the question is, how do we combine it? So for the memory module here, we are using again the top K attention, and now we have these two terms. What we did was we simply just use a gating mechanism. This means that we use a gate. This gate is a scalar. It's a learnable scalar between 0 and 1. so that you can now sort of gate between whether to use the current context or whether to use the memory. So the way we make it between 0 and 1 is that we're just using a sigmoid function to keep it between the value 0 and 1. So this sort of concludes the entire architecture. And I guess
what is the gate a function of?
Oh, gate is a function of a learnable parameter. It's a scalar.
Well, I mean, is it just a global single scalar for the whole thing, or is
yes, it's a single scalar for each of the head. So there are there are probably like 8 heads or so, and you have you have a one scalar for each of the head. Yeah.
Good.
So okay, I want to pause here and see if anyone has any questions about the architecture.
I'll ask a question about the scalability of the memory.
Sure. Yeah.
If I want to do the whole lean library, MATLAB,
Mm-hmm.
is that the kind of scale you're thinking about? Could I think of this as being very large? Then another question, a related question would be, I can think of that memory now as additional model parameters.
Yes. Mm-hmm.
Do you have in mind maybe making these models smaller by virtue of the fact that they have this memory? Or
totally. I think these are very good 2 questions. So first thing about how large or how scalable it is for the memory. At the moment, for the paper that we put out, the memorizing transformer, which is accepted to iClear this year, we put the memory on a TPU. So we didn't use these like very fast implementation of the k-nearest neighbor search. We used sort of our own implementation of top k, which is optimized to do top k on TPU. So basically, in this case, we are able to we are sort of bounded by the memory bandwidth or the memory size of a TPU, which is about 16 gigabytes or so. So that is roughly equal to something around 200,000 tokens, or at most, I think 500 tokens, 500,000 tokens. And that is not able to fit in the entire, for example, the Lang MATLAB library. However, the reason sort of the first paper is sort of really just trying to propose this architecture, and you can probably imagine that here at the moment we're developing a more scalable version of that, which uses these kind of fast implementation, and we can put those memory not on TPU but on, let's say, CPUs or even disks. So in that case, you really don't have much constraint on how large the memory is. So so in a sense, the goal, the original goal was to sort of put all the MATLAB library into the memory here. But it can essentially do even more than that. For example, we want to put, for example, the entire archive into the memory, or even the entire internet potentially. But this is for the future. But yeah, so this is sort of a more of a long-term vision, but or not even very long, because I think we're very close to it at the moment. So yeah, maybe in the next few months or so, you probably see a sort of an upgraded version of this architecture with a much larger memory size. So for your second question about whether these can be treated as parameters, yes, definitely. I think those are parameters that potentially are much more easy to be scaled up. So that's one of the advantage of using memory. So these are like sort of more of a semi-parametric parameters, and scaling these up, it becomes actually more cheaply than compared to if you really just use a dense model. And you will see later in the results section that these parameters or the memory actually allows you to use a small model, but achieve sort of similar perplexity with a large model.
Sounds great.
Yeah, cool. I saw Marcus there. Hey, anyway, okay, so let me go ahead. Okay, so up to now, I think I sort of finished the introduction of the discussion on the architecture side. So I will show, I think, basically the results. And mainly what we are doing here is to evaluate on the language modeling task. And so let me just briefly explain what the task is, just to, to explain basically why this is relevant for our purposes of like mathematical reasoning. So language modeling essentially is just modeling text and modeling, let's say, a distribution of text. And what you can do is, given like any sort of text, you can just pick out like a sentence, and you want to sort of try to predict the next token given all the previous tokens. And for example, here we see here this is just one particular theorem that I sort of picked out previously, and you can see that you also need to predict the use of lemmas. So for example, you need to predict the next lemma needs to be used. The next lemma name is something like 3.12, which is already a very non-challenging, non-trivial problem. So essentially, if you train on these language modeling objective, you are also doing some sort of premise selection. And again, this problem wouldn't be easily solved if you don't have this knowledge base access, if you don't have the access to this large knowledge base. So this is why we picked this task. We think this is a very generic task, and also it has huge impacts. For example, the GPT-3 model, which is a general language model that can do lots of various different text-based tasks, is also just a language model that's trained using this single objective. So yeah, so essentially this is what we're mainly evaluating on. And what we did was we evaluated across 5 different data sets. And we do see we get a consistent gain when we increase the size of the memory. So here the metric is using perplexity. And the lower the perplexity, the better the language model. So perplexity essentially is the cross entropy loss in some sense. It's the exponential of cross entropy loss. So we're seeing here, these are perplexity of 3 different data sets when you don't have any memory. So this is the vanilla transformer, and the 3 data sets here are arXiv math papers, Github, which consists of code repositories. So what we did there was we, for each of the repository, we ordered them, and we basically form a long sequence that contains all the files in the repository. And we want to model the entire repository. And for Isabelle, so for the formal math library, we picked the Isabelle, the arXiv of formal math. And for what we did was something similar to GitHub, which is on Isabelle, the AFP website, there are these different entries. So each of the entry correspond to a theory of math library. So it could be something like knot theory or topology. So each of the long documents essentially is a long theory. It's a concatenation of all the files in that particular theory. So here we are seeing like this is the performance or the perplexity of a vanilla transformer. What if we add in some memory? So if we're adding, let's say, just 1,000, actually in this case it's 1,500 memory, it already shows a big improvement in perplexity, and you can then add in 8,000 and 65,000. You can see a consistent gains when you start to make your memory larger.
Maybe you said when you add things to the memory, you finite size, you have to throw things out. Do you do
Oh
that?
yes, that's right. That's right. So I didn't explain that part. Yes, that's a very good question. So essentially, this is like a rolling buffer. Essentially, we keep the most recent 1,000 keys and values, and we throw out the old ones. Yeah.
The least recently used.
Yeah.
Okay. Yeah. Got it.
Yeah.
I have a question about train versus test. When you're, using a long memory like this, it seems a little tricky to separate the test data from the training data.
So
you don't want to be memorizing anything that's from that you're using then in your validation or test data.
Yeah, so I think the memories, so we clear out the memory once we start to read a new file or new document. So there's nothing that's actually memorized across training to test. Like during training, we will be basically using, we will actually also clear the memory once we finish reading one long document. And once we start to read, let's say, the next repository, we will start from empty memory.
Yeah, this would be more of an issue if you were memorizing all of MathLib.
Yeah, exactly. Yeah, that's right. So so I think also I just want to point out there was another work called Retro from DeepMind, and what they did was also they have a very different system, but they sort of try to achieve similar things. Essentially, they put the entire Wikipedia into their memory, and they did a lot of these kind of evaluation of whether there's leakage from training to testing. And you're right that essentially they do find lots of like a collision between or leakage between train and test. But this is not, I think for now, for this paper, we don't have that concern here.
To understand the benefit of that 1K memory, which if I understand that's half the window size, is that right? How much better would it get if you used a 3K window size instead of a 2K window size?
Okay. So that's a very good point, because I didn't mention that here. The no memory here was actually only 500 context size. So 1,000 is already twice as the context size. So I think, sorry, I didn't pick up your question about the 3,000 memory.
Yeah, so I guess there's a question of what is the relative gain compared to like extending the window size by 1K versus the memory by 1K? Obviously, the memory is much more efficient.
Oh, I see. That's a good point. So we have those comparisons in the paper, but I didn't show it here. So essentially, so let me make like a more explicit. So essentially, we have, let's say, a 512 context window, and then we add, this 1536 memory size, and then we compare that with a 2048 context window. So essentially, these two have exactly the same size of the context. And then we do find that actually these two are very similar in terms of complexity across all the tasks. Yeah.
Cool.
Yeah. So it sort of shows you in some sense that maybe you don't need to backpropagate, like the backpropagation is not as important as if you just have access to these, keys and values that are generated in the past. Okay, so those are like the three data sets that are more on, code or the formal side of things. We also have results on the more natural language style data sets. These are English novels. Essentially, in this case, each of the long document is just one entire book. And also the webtext, which is just general webtext. It's a data sets collected by Google, and it's called C4. And for C4, we so one thing to note here is that for C4, because it also contains lots of the short documents. So for this experiment here, we filter out all the short documents that are shorter than 4,000. So that we can actually the data set becomes more meaningful if we want to sort of evaluate the effect of long context or these knowledge-based systems. Okay, so yeah, so here I'm just trying to show you like memory helps across 5 data sets, and if you increase the size of memory, you do see a consistent gain. However, you can also see here, like the memory, we do see a diminishing return if you increase the size of memory larger and larger. And this is expected because yeah, the information is most dense in the most recent tokens. Another thing that we showed is that memory also can help consistently when you scale up the model size. So here, the experiments, so this is showing like a scaling law for the vanilla transformer on the math papers, the arXiv math papers. We started from the 200 million model and we scale it up to 8 billion parameters. And it's expected that for the transformer models, the larger the model size, the better the perplexity. So you see the decrease of the perplexity over when you scale up the model. So what if you add up 8,000 memory to the transformer model? You can see that now basically the 8,000 memory will improve each of the model for each of the size by a significant amount across different model scale. So this shows that, yeah, like even if you scale up the model, it is still useful to add the memory to the model. And this is probably expected because these are very orthogonal, two orthogonal kinds of improvements. One is just generally a better language model, and the other is that you just give it a more context information, more knowledge for it to make use of, to utilize. And interestingly, I think this is also one of David's point, which is here that you can see that now if you use like 8,000 memory, you can basically attain a result that is sort of comparable to a model that is 5 to 8 times larger if you don't have memory, without memory. So I would say that these two, I mean, even though like the perplexity are matched, I think the model behavior might still be very different. One potentially can make use of more of the context information to achieve that kind of perplexity. The other may be more better at predicting, in general, like the language modeling ability. So even though we can trade off the parameter counts using memory, but I do think there's still also a trade-off. Like we probably still, in the end, we want to have like both. We want to scale up both directions. And one more interesting thing we found is that, so pre-training these large language models is very, very expensive. So for example, if you just train a GPT-3, which is without the memory, and now if you want to train a memory system, do you need to train from scratch? Training from scratch is just, it just takes a long time and also a huge compute. So basically what we showed here was that it is actually possible to take a pre-trained language model and you can just add this memory to it so that, after only a few steps of fine-tuning, you can get the kind of improvements or the kind of benefits you have if you have trained this model, the memory model from scratch. So this curve here shows 3 different curves. The red one and the blue ones, these two are essentially training from scratch models. The red one is the transformer, the vanilla transformer. The blue one is the model that's augmented with a 8,000 memory. And you can see that here the blue model achieve a better perplexity than the vanilla transformer. So what if I take this transformer, the vanilla transformer, and then I sort of initialize the weights and we add, if I initialize the weights with the vanilla transformer after pre-trained, and then we add a memory of 8,000 to it, and then do a few steps of fine-tuning, this is what we get, like this black curve of this very steep descent in perplexity is what you get if you just add the memory to it. So this does shows that like the learning doesn't it doesn't require too much learning in some sense to make use of the memory, because the keys and values that are trained are already pretty good, like during the language modeling training, so during the pre-training. And all you need is probably just to learn those like gating functions or the queries, or basically trying to train how to query from the memory, and those probably doesn't take you too long to make it useful. So this shows you like essentially it's very convenient to use such memory. If you have like already like a pre-trained model, you can probably just add a memory to it to achieve a pretty good to sort of make use of the extra knowledge base. And okay, the last thing I want to talk about is and this is something that people also have pointed out earlier, that if you have a really large memory, if you just during training you just still do this like looking at a chunk of the sequence at a time, and you do optimization steps between those steps, and this will create a problem, which is the memory or the keys in the memories will be generated from an old set of parameters, and this may not be exactly the same or may not be directly usable for the current transformer. And therefore, we do see some kind of instability when we increase the size of the memory to a very large size. And here, it turns out that you can also do the same kind of fine-tuning trick to make use of a large memory. So what this means is that you can again, train a model potentially with a smaller memory. You can then, during the fine-tuning time, you can then increase the size of the memory. And it turns out this is actually better than if you just train from scratch. And if you do this, then you can see we can see gains if you increase the memory size up to something like 262,000 tokens. So let's even take a look at what this means on the scaling plot. Actually, the 262,000 model can attain a result that is quite comparable to the 8 billion model. So essentially 200 million model with a 200,000 tokens can be comparable, not exactly the same, but comparable to the 8 billion parameter model, which is 40 times larger. So this again shows you like, the kind of benefits you get if you increase the size of the memory. Okay, so lastly, I think I want to go back to the original sort of motivation of why we want to have some mechanism like this, right? Like the original motivation is to somehow make use of this to predict the lemma name when we do the theorem proving. And we hence go back and we look at exactly what the memory retrieve when they try to predict some lemma name like Markov inequality. And what we found out is that they actually look up the definitions, which is 20,000 tokens before this proof. And again, this is something that the vanilla transformer cannot really achieve. And something more interesting is that they look up this particular particular context, which is of the same structure of something that is in the context. So we suspect this is why the model looking at this, it's sort of matching up some kind of patterns, and it helps the model to sort of predict the lemma name. And this again shows you like the non-trivial capability of this model. Okay, so all right, so basically let me summarize. The takeaway is that the memory is a very generic model. Essentially, we see gains across various kinds of domains, including the formal type of text or the informal natural language type of text. We also see the scalability aspect, which is this memory module can be scaled up, and also it consistently helps the model even if you scale up the model size. And we also see the most important or the most interesting aspect, which is this utilization of the lemma names, or sorry, the new knowledge facts that are acquired. So so just to look into the future, I do think memorizing transformers show a lot of promising directions. And first of all, as we also talked about this already, at the moment in this work, we are only memorizing a long document. We can expect if you scale the size of the memory up, we can memorize beyond just a long document. We can memorize the entire theorem database, let's say the mathlib library, or we can even memorize the arXiv or even the entire internet. And on the other hand, there are many things that can be improved for the existing system. At the moment, we are doing this retrieval at each of the tokens. So like we are doing like issuing this query at each token. And this may not be necessary, right? Like you think about how human look up text. We probably read a long text, and then we think about, okay, what kind of information we need. So we look up books or so. And that's why maybe there are many more improvements we can make to improve the efficiency of the system by, for example, specifying the retrieval, or using like a chunk style of memory, or improving the forgetting mechanism. We're at the moment only just doing the most recency style forgetting, but potentially we can sort of compress it or learn a compression model for the memory. Also, potentially this model can be even augmented with new kinds of capabilities, such as, you know, if you include recurrence. So what this means is that at the moment, the memories we generate is not a function of the past memory. So these are like, when you read the same sentence twice, you always see the same keys and values that are generated. We want, so ideally, we want, you know, the capability of potentially reinterpreting these memories based on what already has been in the memory, right? So when you see the same thing twice, you probably have a different interpretation of the same thing. And this can be probably augmented with something like recurrence. And also, potentially, we want to have more kinds of hierarchical structures for the memory. Instead of just have like a flat memory structure, potentially we can have the token level memory, the document level memory, or like, I don't know, like some kind of higher level structure of memory, so that it becomes easier to be looked up. Lastly, I just want to point out that this module of this memory model here it could be useful for not just, you know, the text-based type of tasks like question answering, or, you know, what kind of things we do here, which is theorem proving. But more interestingly, you can even think about, you know, applying this to, let's say, image generation. So what if you have the entire internet of images in your memory, and then if you want to, you know, if you have that, you probably can more easily generate a new image or a new faithful image. Or even think about general reinforcement learning, where you can put the entire experience replay into your memory, so that when you decide what the next action you want to take, you can look up the past trajectories that are most relevant, and that can be used as information to predict next. Anyways, those are things that I'm currently exploring, and hopefully, yeah, I guess if you guys are interested, I'm very looking forward to more discussions on them. Okay, so I will conclude my talk here, and thank you very much. And again, thank you for inviting me. And yeah, if you have any questions, you can ask me now. Yeah.
Thanks, Tony. Great talk. Questions from the audience?
Thank you for the great talk. I have two questions. One is, so you showed this improvement on the language modeling task in terms of perplexity, but have you tried like downstream tasks, like for example, classification or theorem proving?
We haven't yet tried, but this is our next step. For the first work that's presented here, we're just showing, the general capability using language model, which we think is the most general task that already can be meaningful to show the benefits of using memory. Yeah.
I see. And another question is like, so you compared with the basic transformer, what the generic transformer, but there are other work trying to make transformer able to handle non-context. For example, some of them they use kind of sparse attention rather than dense attention. So like, how does memorizing transformer compare with this line of work?
Right. So first of all, I think in our paper we do compare to some architecture like Transformer XL. The reason we didn't do like a full comprehensive comparison to all those previous long context work is because we think it is not a long context work. It is more about storing the knowledge base, because this is the kind of work that really can allow us to scale up to huge context. Whereas the previous method, for example, even if you have a linear transformer, it's really not clear how do you scale up to the entire archive or the entire internet. So we do believe this is a new kinds of capability. So that's sort of so that's my response to that.
Thank you. That makes sense.
I have a sort of a technical question that I may have missed. Are you doing this for every head at every layer, or are you?
Oh yeah, sorry. This is something I forgot to mention. Yeah, so we only do this in one layer of the neural net, which is something which usually seems to be the best around the middle of the entire transformer stack. And about the number of heads, so that is an interesting question, because I also did some ablation study, which wasn't included in the paper, but yes, you can actually only use like a few number of heads. So the memory, the lookup heads can be much smaller than the usual number of heads that you use to process the current context information. So usually, for example, if I use, let's say, 16 heads for the vanilla transformer, I only need, let's say, 1 or 2 heads for doing the memory lookup. But still, in this work, we didn't explore, we didn't include that result. So like all the experiments I showed you here uses the same number of retrieval heads as the usual number of heads. Yeah.
All right, I have another more speculative. Thanks, that was good. Another more speculative question. If I think of this, if I think of your memory as model parameters, right now the memory is, each memory entry is derived from some token somewhere in your corpus. But if I sort of broke that attachment and just treated it as a memory for the language, I initialize it that way, but then just treat it as more parameters of the model, which you continue to tune. Yeah, it would sort of disconnect the memory from the data in some, or it would be more indirect and more just like model parameters. Have you thought about that direction?
I think, Marcus here really had have been thinking about that direction as well. I mean, we were thinking about potentially how to backpropagate into the memory, and just the easiest way is by just treating them as the model parameters, so we can just do a little bit gradient descent on these keys and values. So those are very cool ideas. I think one of the other interesting line of work is something called persistent memories from Facebook. And what they did was they actually introduced these learnable parameters, the learnable keys and values, into the memory. And they really just made them learnable. So like essentially, you don't even need the intermediate MLP layers. You just need those extra learnable keys and values in your memory. And those can be used so that you can sort of store information there as a learnable parameter. And I think these ideas can be combined together. So maybe your memory has a group of learnable parameters or learnable keys and values, and the other is like you're just storing all the facts and informations like what we do here. But yeah, so that's a very interesting direction in the future. Yeah.
Great, thanks.
I think there's a question in the chat, or okay. Oh no, Daniel. Thank you, Daniel.
More questions, or
I have a brief question about the scaling behavior, if that's okay.
Sure, sure.
So I remember you showed the scaling plot.
Yeah.
Where it seemed like adding the memory shifted the scaling curve down.
Yes.
Were you able to observe any change in the scaling exponent due to adding the memory?
No. So that's not. No, I think it's mostly just a shifting, a constant shift, and not exponential, not exponent change. So yeah, at this point, yeah.
Oh, interesting. So also, if you take the perspective that the embeddings in the memory are merely another form of parameters for your model, have you been able to calculate some kind of conversion ratio, right? Like you could imagine, like you could treat like 1 billion bits of embeddings as like 0.6 bits of like actual transformer like floats, right?
I still don't think they're entirely equivalent. Again, for the point that I think they're used for different purposes. So I'm not sure if this kind of conversion.
Sure, but in
really
terms of the
makes
scaling
sense.
plots, right? Like if you like train a really big dense transformer, then there's like some increase of the size of the transformer used to create the red line that produces something that looks like the blue line. And so maybe there's like some kind of constant or scaling behavior that controls like when a large enough dense transformer will achieve the same performance as a transformer with an external memory store.
I'm not sure. So again, I think you're sort of only talking about the perplexity measurements, right? Like whether we can achieve the same perplexity either using, increasing this model size or using, this external memory. So my point is that I think even though they achieve the same perplexity, maybe the models are still very different. So it's not super meaningful to talk about like, you can just convert like a dense model to a model with memory, because I do think even though they achieve the same perplexity, but they might making different kinds of mistakes. One is just, a better model for referencing knowledge in the knowledge base. The other may just be a generally better language model. So that's my point. So if you look at, for example, like a cross entropy plot for each of the token, my expectation or my prediction is that if you increase the model size, you probably get a constant shift or a shift down. You basically get a uniform improvement over all the tokens. But if you use memory, you get most improvements on those tokens that are trying to refer to the information in the knowledge base. So I think these are still two different kinds of or two orthogonal kinds of improvements.
Yeah, for sure. Perplexity certainly won't capture the qualitative delta. So another question I had along these same lines is, do you know if do you have a quantitative measure for how much more compute efficient these transformers are?
How much more compute efficient? So I guess so at the moment. Okay. So for these memorizing transformers that the experiments that are done, especially for this plot here, if you only use an 8,000 size of memory, you at each time step you only increase the walk clock time or training step by only like 20 to 25%. So like in terms of the flops, I think it's really similar like in this case. So yeah, so I think I guess
yeah, this is just related to my earlier question of like what is some kind of numerical conversion ratio between like just viewing the memory store as a form of really sparse attention compared to just having more parameters in a dense model, because like maybe the things in your memory store aren't as good as normal dense parameters, but the increased compute efficiency makes up for it. And so maybe you get some kind of nice relation between them. But this is just more speculation.
Yeah.
Thanks.
Yeah, let's discuss that offline, Jesse. Yeah.
Okay. So if there aren't further questions from the audience, let's thank Tony for a really very interesting, enlightening talk.
Thank you.
And this is the last of our new tech seminars for this semester. Thanks everybody for joining us. We'll start again in the fall on September 14th with Johan Kummelin, who will tell us about the liquid tensor experiment. So have a good summer, everybody, and I look forward to seeing you all then.
Thanks, Michael, for organizing everything. Thank you.
Thanks. Thanks.